geological and geometallurgical modeling, and data analysis. Further information can be found in at this LinkedIn address. Okay, this is our agenda in the Santiago Chilean time. After opening, we'll review a half-an-hour presentation. Afterwards, from 10:10 to 10:40, we will conduct a project for a preliminary definition of geometallurgical units using Orange data mining software. Finally, we will have about 15-20 minute session for question and answer as indicated by Abdul. Our roadmap for today. First of all, we will discuss about geometallurgy and data mining definitions. Secondly, we will explore the database to be used in the project. Then we will review how clustering, a set of machine learning algorithms, works. Finally, using our database, we will carry out a project in Orange data mining for obtaining preliminary geometallurgical domains. This is our goal. Okay, let's move on. Okay, definitions. According to Wikipedia, this is the definition from Wikipedia. Is here. You can read it. The important thing is that geometallurgy is mainly based on these three vertices: geology, metallurgy, and mining or mine planning. These three must be strongly integrated. Additional definition of geometallurgy can be found in the previous workshop. Okay, this slide was shown in the previous workshop as well. This is the stages for obtaining a block model with geometallurgical information. In a sequence, starting from the left, design and selection of samples. Secondly, the metallurgical test work and complementary characterization. Modeling, starting from EDA or exploratory data analysis. And finally, estimation of the metallurgical parameter in the block model. Generally speaking, these stages are quite similar to those used in grade estimation. This workshop will be focused on modeling, which is highlighted in blue in here in the slide. Can you see my pointer?
Yeah, we can see your pointer.
Perfect. Let's move to data mining definition. First of all, mining industry count nowadays with or on massive databases, including data such as logging, assays, mineralogy, geomechanical, metallurgy, and so forth. All of these are high-cost activities. However, a question for everyone: do we take advantage of all this data? Well, Here, another definition from Wikipedia. Data mining, an interdisciplinary subfield of computer science and statistics. Okay, so this is the definition from Wikipedia. You can read it directly from the slide. Important thing to bear in mind, data mining does not search from the mining industry. Okay, so this is more than mining industry. Why it's called data mining? Because it's related with the extraction of variable information of ore, shall we say, our ore. Our ore in this case is information from a mountain of massive databases. Okay, this is the relation between mining and data mining. So it's in the beginning was nothing to do with miners. Okay. Data mining has 3 vertices as well, shall we say. This triangle, the statistics vertice, related with the collection, organization, analysis, interpretation, and presentation of data, as we know. Machine learning, related with computer algorithms that improve automatically through experience. And finally, database systems, which correspond to an organized collection of data. Well, for developing a proper data mining project, what we need? We could use this or consider this scheme. Firstly, we could start in understanding our business. In our case, for this project we want to conduct today, our business is a copper leaching operation, okay, where acid consumption is an important parameter. Secondly, we need to understand the nature of our data, types, ranges, among others. After this, it's relevant, it's important to prepare our data. Eventually, we will need to correct, transform, imputate, or remove part of the data on this stage. Then, modeling will allow us to explain, classify, generate regressions, or in our case, cluster our geographical, assay, and mineralogical data. Finally, the evaluation will permit us to the deployment of the model. Okay, good so far. Where we are in our roadmap, we pass already the definitions, so let's move to database review. Our database. Okay, this is a subset of samples of our database. Okay, please take a look at the database. This is the database to be used in our project today. This is a modified actual database that contains 15 variables or columns and 220 samples or rows. These are geometallurgical samples. Okay, these samples came from drill holes. variables are divided by type. The first column or variable corresponds to sample number, okay? So we are showing in here from 149 to 162 samples. In green, variables coordinates, okay? X, Y, and Z variables coordinates. In orange, we have 3 acids: carbonate, iron, and sodium. In purple, mineralogy, look at this, totaling 100, okay, 100%, 100% of the rock. And finally, the metallurgical variable corresponds to acid consumption, which is our target variable, okay? I would like to make a question. Just please think about it. Do you think this database is ready to use, or maybe it is required to modify it, additional work on this database? Okay. First of all, look at this. What is this? Symbol like greater than needs to be removed. Okay, first, previously to any math operation, we need to remove this type of symbols. This type of symbols are typical, as we know, in our databases. And these values, look at this, minus 99. What happens if we sum up or add this or average or weight this type of figures with these others? We're gonna get a mess probably. So we need to understand our data as we previously discussed. Prepare the data is key. So we need to remove this one from our data. And finally, look at this. We need to understand our data and identify what's wrong. If we understand our data, we cannot tolerate, accept that rock is 0. Okay? It's like, what happened here, man? So probably this is error. So someone inputted these zeros by mistake. I've seen this one in the real world. So take care, because imagine making a modeling when you put zeros in the drill holes, but indeed they are not zeros, they are null. It's very completely different, okay? And a last comment about our database, or general comment, is data preparation is a key stage for data or data analysis, okay? Okay, our target variable. Metallurgical data, acid consumption. Well, where the acid consumption data come from? This parameter is obtained from a metallurgical laboratory test called bottle roll test. In this 1 kilogram of sample, 100% under 2 millimeters granulometry, is put into a plastic bottle with 2 liters of acid solution. The bottle spins at 20 RPM. pH is kept at 1.5, adding sulfuric acid when required. Finally, it is calculated the acid consumption of the sample. Important thing to remark in here. Sulfuric acid corresponds to about 10% of the OPEX in a bleaching plant. Okay, the cost in this input nowadays is about $100 per ton. So the message in here is this is a very important input in the mining industry for leaching process. Okay, let's check a video. It's the same bottle, the same spinning bottle. Look at the inner of the bottle. We can identify here the liquid phase and the solid on the bottom. Okay, this is where our target data come from. Okay. Okay, let's take a look now to distribution of our samples in the space. This is a plan view for our samples. Okay. And looking north view in this other on the top right. All these samples came from drill hole. Okay. Continue with our roadmap. Let's discuss about the concept of clustering. Our friend Wikipedia again regarding Wikipedia task. Clustering is a task of grouping a set of objects in such a way that objects in the same group are more similar to each other than to those in other groups. Take a look, please, in these animals. We can split or cluster or group these animals by separating between extinct and living ones, or even like blue ones or gray, or even change this to animals from the ocean, from the land. Okay. For this development, we want to consider using two clusters, the k-means and the hierarchical clustering. Okay. So let's review the k-means. Let's consider this bidimensional space of x and y variables, x and y. In this space, we display these 12 samples. Let's generate 3 clusters with these samples. What is to say, we want to put these 12 samples in 3 bags, shall we say. Okay, first of all, we need to put how this algorithm works. First, we put the centroids, the geometrical centroids of the clusters in a random location, okay? It's only a random location. And we cluster our sample as red, green, or blue cluster in this way. How? Only based on distance. So this sample, the red one, is its closest centroid is the red. That's the reason, because it's red. Okay. Now we have the clusterized samples let's iterate this process, move the centroid to the centroid of the cluster. So let's move it. Okay. And now we have different cluster. We iterate this process up to cluster remain, shall we say, stable. Okay, this is the k-mean clustering concept. Looks, someone maybe can say, oh man, this is really simple. I can do that visually. Yes, I agree with you. But what if we don't have only 2 variables? What if we have 3? Yeah, it's possible to do it. But what if we have 10? Can we imagine a 10-dimensional space with scattered samples? Yeah, probably it's complicated. Am I right? Let's move to that was the k-means. Hierarchical clustering, the base is more or less the same. It's distance between samples. Distance is, when we talk about distance or space or geometry, we are talking about this space, the space generated by the variable x and the variable y, okay? Could be an assay for us, a geological parameter or metallurgical parameter, geomechanical parameter, whatever, okay? Okay, the similarity in this case, in the hierarchical clustering, okay, is expressed in as a dendrogram. So we want to have this space on the left, on the right, dendrogram, okay? Let's compare what happened if I evaluate the clustering. For instance, these 2 samples, AB and DE, are the closest in this space. So we generate cluster, can you see? And dendrogram. Okay, let's move to the next level. After this, we have the C sample, and we can generate another cluster, the green one. And how this is expressed in the dendrogram, like this. Can you see it? Let's continue. What's next? F with DE. So our lavender, shall we say, lavender color, lavender cluster, and dendrogram is that. Can you see the distance and similarity approach? Finally, these 2 clusters, the green and the lavender, can be grouped or clustered like this. So this is the way that hierarchical clustering works, but basically it's very similar to the k-means. Okay, they make similar kind of work. The approach is very similar. Okay. Well, what time is it? It's wait. It's 10. Okay, we are okay. Let's move in our roadmap to the project development. Orange data mining. Study case through Orange data mining. Okay. Let's move to Orange. Can you see my screen?
Yeah, it's
with
clear.
The orange?
Yeah, it's pretty clear. Yeah.
Thank you. So, This is Orange data mining. Let me introduce you to Orange data mining. Orange data mining is an open source data visualization, machine learning, and data mining toolkit. Orange components, this one on the left, are called widgets. And they are ranged from simple data visualization, subset selection, and pre-processing to empirical evaluation of learning algorithm and predictive modeling. Orange consists of a canvas interface, this one, the white section, onto which the users place widgets like this one. This one. Okay, it's very simple. And in here, we create our data analysis workflow. So let's start with import our database. So we can drag our widget, okay, or right button. Okay. File, double click. And Orange is like in any other software. We can get our database from here. What is this? What is this? This database is our preprocessed database. First column corresponds to the name of the variable. As we can see, this is the same variables we previously reviewed: sample, coordinates, the metallurgical variable, and assays and mineralogy. Second column represents the type of variable. In our case, all our variables are numeric, but you can select in here if you want to change it. Categorical, like lithology or path of a leaching, or sack or ball mill number 2, text or time. We need to change this one to numeric. All our variables are numeric, yes. And the third column represents the role played by each variable. Sample, in first place, sample is considered as metadata. Why metadata? Because we don't look for this variable to be part of the analysis. Am I right? It's only sample identification. So it's a metadata. Sorry, metadata. Drink some water. Metadata. And our target variable, we need to identify, in this case, our target variable. Target variable is, as previously discussed, acid consumption, okay? And all others are features. Features are variable that we will use for the afterwards analysis, okay? So once we define our variables, we can just apply, okay? So I'm gonna just close. Then we have our variable. Let's move. Look at this. We can take from this one with the left button and create a connector with other widget. Okay. Or if you want, you can just drag it and connect it. Okay. There's no problem with that. And let's have a look on our database. So double click data table. This is our database. By convention, as usual, columns represent the variables. Okay. The first one in gray is the target variable, our acid consumption. The second is our metadata, and the others are features. The length of each var is a representation of the relative magnitude of each particular variable and case. Okay. So if we have a look on this, we can read the quartz content, for instance, the sodium carbonate, and coordinates all this nice bunch of data. So perfect. Let's move now to another widget, which is preprocessed. So we can even write in here, preprocess, and now we want to preprocess our data. Okay. This, we need to move this one and this. Okay. Preprocess. Why? Let me show you. Double click and we can preprocess our data. In our case, we would like to normalize our features. Okay. Which means standardizing to means 0 and variance 1. Okay. So let's have a look in the preprocessed data. But first, let's rename this variable. We can call this preprocess data. Okay. And now we wanna, after preprocessing, sorry. Let's have a look on the preprocessed data. It's same structure. Can you see? It's the same structure. Features has the same statistical distribution. It's the same shape, but all our data is transformed. Why transform? Because for the next widget, we can't compare different variables with different magnitude, like I don't know, coordinates with 100,000 versus iron grade, iron assay with 0 point something. So for that reason, we normalized. So now we can have this more or less same scale information, same scale data. And the widget we would like to use is heat map. Okay? Heat map. Okay, heat map. Heat map widget is useful for conducting a preliminary evaluation of the relationship between our samples and variables. Double click. And okay, this is a result of our heat. This one, okay. This is our heat map. Heat map is a graphical method for visualizing attribute values by class in a two-way matrix. Two-way, one way and the other. The values in here are represented by color. At the beginning, this chart can be a little bit difficult to interpret, even though let's take some time in understand this interesting chart. Firstly, columns correspond to the variables. Remember our variables. Our 11 variables, okay? These variables, as you can see, are grouped. How? Remember this one? They are grouped using hierarchical clustering. So, a first interesting thing can be recognized. Two clusters of variables arise, one on the left from sericite to quartz, the other on the right from sodium to elevation. So rapidly we can identify two clusters of variables, okay? Secondly, rows, the rows are our samples, also grouped through hierarchical clustering, which is shown in here. Okay, one can do this type of selection. And another interesting thing, it's possible to identify here samples, as you can see, based on my interpretation, obviously, can be grouped in two major clusters. This one, the upper, and the lower. Okay, the lower and the upper. Maybe you are identifying the same as me, and the upper cluster, this one, is characterized by this type of variables. These variables on the right cluster, like higher values of carbonate, siderite, all of these variables. On the other hand, we have this the lower cluster with these variables. And this cluster is dominated by variables on the left, like sericite, iron, or quartz. Finally, let's have a look on the target variable. Target variable is not used for clustering, okay? So let's have a look on the here in I think it's in here, yeah. In annotation and legends, in color, we add this acid consumption. okay, which is the column on the right, okay. Column of the right, on the right, and look, please, like the upper cluster, this one, in general, is really related to higher values of acid consumption. Okay. And the lower cluster is related with lower values of acid consumption. So this is, I would like to say that this is a very, in my opinion, my humble opinion, is a very powerful way of showing our data. So it's a really good option for you people. Okay, let's move to the second part of our analysis. Let's make a k-means clustering. So this is hierarchical, based on hierarchical mainly, and this is for k-means. Okay, k-means. So double click, and we have this dialog. Okay, number of clusters. How can we define this? Well, we can select a number of cluster or ask to, or using this silhouette score for selecting the best option. In our case, probably our best option is 2, based on the silhouette score. So silhouette score is showing how good is the classification or clustering. Okay, clustering is the best word to use. So we have 2 clusters in our exercise, and please consider that we have this option in here, pre-processing, normalize columns, okay? So we don't need to start from pre-proc because we have this option of pre-processing here. And close. That's it, it's ready. Let's visualize the result of our 2 clusters using FreeVis. Okay, FreeVis. Another useful tool from Orange data mining. Double click and from the beginning. Okay. Here we have a project of our 11 features. Remember, we are working in here considering an 11 dimension space projected in this bidimensional representation. What is this? We have our features as vectors, okay? Is siderite, cerussite, and our projected samples. Here we have our almost 200 samples in here. Okay, what happened with our clustering? Let's check how our cluster works. So in color, we select cluster. So this is the result of our clustering, but this is not the best site of the information. So we change to the direction of maximum variability to look at the data. Okay, so press start, and ta-da! This is our new visualization. This maximum variability direction. So something very remarkable has happened. We have now variable strongly pointing to the left, like this one, like feldspar, carbonate, and other pointing to the right. So it's very beautiful example. So they are very, very different variables. In addition, samples are almost perfectly split in this space, with cluster 1, the blue samples on the left, and cluster 2 samples on the right. We can also review or color the regions for each cluster, like this, if you want to check it. Okay. Finally, what happened with our target variable? We can add or display the size of this circle in here in size. Okay. And proportional to the acid consumption value. Okay, so in size, choose acid consumption, and look at this. What happened here? It is possible to recognize the highest acid consumption values located to the left. Okay, related to the features siderite, carbonate, feldspar, for instance. Conversely, the lowest acid consumption values are found on the right, associated with the features iron, cerussite, quartz, jarosite, and coordinate or east coordinate in here. Finally, we are cool, probably. Please have a look, final look on this. I'm gonna close it, and let's check the result, additional checking of our result. This is the last widget I would like to share with you today. Box plot. Okay. In box plot, this is box plot. So select in the lower part, in below here, we have the subgroups cluster, and variables. We can select cluster. In this case, to identify the number of samples by each cluster. So cluster 1 has 73 samples, and cluster 2, 123 samples. Okay, let's check the acid consumption by cluster. here we are. We have. So cluster 1 contains samples with an average acid consumption of 41 kilograms per ton, while cluster 2 includes samples that display half of the acid consumption of the cluster 1. So it's pretty different indeed. In addition, the interquartile range, represented by this blue rectangle, is also completely different between the two clusters. For finishing, I would like to say that we could evaluate additional features like quartz. This is quartz. Or coordinates, east. Look at the east. So we are recognizing in here a different spatial distribution, probably in these two clusters, for the samples of these two clusters. And that's it. That's it, my dears. This is the end of the project. I'm gonna close it. No, just in case, I'm gonna put it down and I'm gonna come back to presentation for finishing. Okay, this is the distribution of the samples, but now split it or grouped by cluster. So interesting thing is we can, in a preliminary, as a preliminary work, we can recognize a probably domain in here on the west, on the northwestern part, this cluster 1 with higher acid consumption samples, and this other, the orange one, with the lowest values of acid consumption. Moreover, we have in here a rare sample like this one. Can you see it? This is a nice opportunity to check that sample and review why this sample was clustered as one cluster, was clustered in the cluster 1. So we can even use this type of algorithm for reviewing outliers or anomalous values. As final words, a multivariate approach through data mining is suitable for supporting geometallurgical modeling, taking advantage, this is very important, of the data available in increasingly larger databases. As we discussed in the previous session, databases in the mining industry in the world, throughout the world, double each 2 years or 1.5 years. So after 1.5 years, we will have double amount of database or information in our databases. Secondly, using tools such as Orange data mining allows us conducting data analysis and visualization in a simple and a useful manner. Bear in mind, please, that the data mining method or approach is a useful methodology for EDA, but it does not replace modeling based on geological domain, such as lithology, alteration, and so forth, as we discussed on the previous workshop. Further reading for you on data mining, clustering technique, and Gracias.
Okay, Christian, that was interesting presentation. I think we still have plenty of times because our target is finishing this one at 11 or in 9 in Jakarta. So approximately we will have like 30 minutes. So guys, if you have any kind of questions or want to discuss with Christians, please just unmute yourself and then ask the question. Or if you don't want to talk, you just can write down your question in the chat section, and then I will read it for you. Okay, while we are waiting for the question, Christian, I have a question. Maybe it will give insight as well to the participant. So here is the question. Since this kind of method, I mean, K-mean clustering, hierarchical clustering is categorized as unsupervised method. So it means geology don't have any right or any intervention during this clustering. Yeah, we do. We can easily determine our domain, or I mean, like if we want make our domain 2, it will simply just make into 2, and then if 3, and so on and so on. So the question is where we should put our interpretation or our geological knowledge during this kind of works, not specifically in this stage, but during these works. Because as long as I heard during your presentation, you haven't mentioned about it. So yeah, that's the question.
Okay. Yes, as mentioned before, this is a complementary tool. So, in my opinion, it could be useful at the beginning, just to check and compare our clustering, for instance, clustering result with our geological or geotechnical domains. Okay, so we can double check these results. In addition, I have applied this kind of tool inside one geometallurgical unit. So it's really useful. It's really good to prove your geometallurgical unit. For instance, if you have one geometallurgical unit or one geological unit or one geotechnical unit, then you can try, you can put this unit under a test. Please go ahead with clustering. And if the unit is completely fine, is well defined, cluster shouldn't show any important difference inside a particular unit. So it's a very useful, in my opinion, based on my experience, very useful tool for validate our geological, geometallurgical, or geotechnical domains.
Yeah, I think that's pretty clear. We have another question from Fisco. I will read it for you. The question is, if we use machine learning clustering, the domain result will be stationary or not? And if the domain stationarity from lithology and geometallurgy different, we need to run the estimation from with different domain? And then the other question is how to choose the optimal number of cluster. So please.
Okay, that was really fast for me, but
Okay.
the first one was
okay. I will. I think this is the simplest one. How to choose the optimal number of cluster?
Yeah, we have several algorithms like silhouette. Silhouette is one of them. Orange uses silhouette. So any scoring algorithm for defining the number of clustering going to optimize, going to show the optimal number of cluster based on the structure of the data. So if you have, I would like to come back to one figure,
Yes, please.
one slide, this one. Can you see it?
Yeah.
Can you see my slide of the k-means clustering?
Yeah, we can see it.
You can?
Yeah, we can see it.
Can you? Okay. So, for instance, in this slide, probably the best option, if you put this data in a silhouette score or other, probably the result of this definition of number of cluster going to be 3. I don't know if the example is good enough. It's clear in this case that 3 is the optimal number of clustering. Okay? It's based on the structure of our data. If you have, imagine, two groups of very separated characteristics, features, or 3. In this case, it's really simple for the cluster to define the number, optimal number of cluster. It's very simple. But we need to say, it's important to say that clustering has limitations as well, especially when we have outliers or we have mixed populations. So it's not necessarily the result going to be as good as we discussing here. Okay, and I don't know if that was the question of Fisco, but this tool, if this tool shows that we have maybe we could improve our geological definition. Okay, this is a feedback. We come back to the geological model, talk with the people of the modeling and say, "Amen. We discovered that, I don't know, quartz is low in here in this northern area, in this high in this southern area, and this is controlling our bond work index results. Can you please check your model and try to improve it for our purpose of in geometallurgy?" A possible approach.
Okay, so is that answering your question, Fisco? Or it's how about stationarity? How about stationarity of the cluster or the domain itself?
In terms of spatial covariance, in terms of variography, or in terms of statistical?
Yeah, I think because Fisco here asking about, I mean, yeah, I get the point. He's talking about variography and statistical in order
Okay.
for the estimation, because we need stationary condition, right, for doing rigging or something. So yeah, that's the related.
I would like to say that in the same example I was talking about, maybe one can have a geological unit for estimate nickel nickel grade, okay? Just saying, nickel or copper, iron, okay? So this is stationary. And we use same for geometallurgy or geomechanical, okay, geometallurgy. And we discover our variable of bond work index or acid consumption is not stationary, okay? And in that case, we can use our clustering for improve our definition of domains. In that manner, we should obtain a better definition or a better unit for geostatistics, a more stationary unit for that parameter. Yeah.
Okay, is that pretty clear? Okay. A little addition for answering about the how to choose the optimal number of cluster. So basically we have two kind of method. The first one is about the visual. This is called as elbow plot. And then the other one is through calculation, like Cristian did in the orange data mining. In orange data mining, he used silhouette index, and then the other one is Davis-Baldwin index, and the other one is Dune index. You can see further about clustering and how to obtain optimum number of cluster in the further reading reference. So we have another question from Tapia Aguilera. In comparison with other areas, example social net data, the number of data is huge in comparison with geometallurgical data. There is not a problem for data mining methodologies to be used in geology.
Yeah, that's a really an interesting question. It's maybe it's not obvious, but it's maybe it's probably exactly the opposite, because considering we have only 100, 200, 500 samples, we have to take advantage of all our information. Usually we have a Geomet sample with ICP, ChemScan, metallurgical result, very extensive amount of data, or columns if you want. And data mining approach allow us using all this information. If not, we are very limited to only 300 results of bond work index. What can we do with that? Based on my experience, we can talk about in the next. We want to talk about this topic in the next workshop. It's the geostatistical approach for geomet variable. It's possible, but not simple. Okay. Proxy approach based sometimes in data mining can be a better way for develop this type of estimation of understanding of our data. So for answering, to sum up to Tapia Aguilera, data mining is more important in these cases because we have few rows, few samples, but sometimes 100 of variables. So let's take advantage of all of this information to make a better approximation to our domain definition.
Okay, I think it's pretty clear. Do we have any other question? No? Okay, I think we don't have any other question, Christian. So yeah, before we end our session, I will remind you again about our next two sessions. If you interested about our third and our fourth, about estimation of geometallurgy parameters in the block model, it will be conducted in November, and then implementation of geometallurgical model in December. So once again, we will mainly announce it through LinkedIn. So if you are interested, you can just follow us in LinkedIn. So yeah, I think that's our session. Christian, muchas gracias. And thanks for all who staying until now. And then thanks for the participant who asked, Visco and Tapi Aguilera as well. So hope you guys enjoyed it and see you in the next time. Bye.
Bye.